models today, and we're going to be talking about first this raccoon rolling down a hallway because it's just very interesting, and it brings to mind a couple of key questions. One of them being, why is a raccoon rolling down the hallway? It's fair to ask. And another one being, what is this raccoon doing in someone's house? I'm actually more interested in that question. Don't kid yourself. Raccoons are basically kind of smart rats, and if this thing is going anywhere, it's probably going to the kitchen to tear it apart looking for food. So, I don't know. I personally wouldn't want a raccoon in my house. But anyway, we're going to ask ourselves some other questions. IB encourages us, and I do think it's a good idea, to talk about the nature of science, which is abbreviated as NOS. So that's going to be kind of a theme, especially as we're starting out here. A couple of questions. What is a scientific model? What is meant by that? And how do we know that atoms exist? I mean, we can't see them, so how do we know that atoms exist? Do we know? Is that even an appropriate word to use, know, that atoms exist? And how do we know what their structure is? So we're going to talk just a little bit about that. We don't need to necessarily know this information specifically in terms of the first thing I'm going to talk about. We don't need to know it specifically. But I think it's good to know about this stuff, and it also kind of fulfills the requirements for talking about the nature of science. So you don't need to write any of this stuff down, but atoms started with John Dalton. Long story short, he basically viewed atoms as a sphere, a ball. And he realized there were different elements, and basically each element was a different size sphere with a different mass. And chemical reactions happen when you rearrange these atoms in different combinations. That's basically what he said in his atomic theory. So this model is really only partially correct, or it's actually very incomplete as we would think about models today, because he doesn't talk about any of the stuff that's inside of an atom, as we now know, protons, electrons, neutrons, etc. So his model is wrong. However, what we have to understand about models is models are just ideas. Our ideas evolve, ideas change over time, but even if they're not completely correct, models can be very useful. And as a matter of fact, I would say about 90% of the chemistry that we talk about in this class, you can really just kind of view a John Dalton type model of an atom and view atoms that way, and you'd be doing just fine. And you can do a lot of chemistry that way. So models change, they get better, but we can operate within imperfect models sometimes. Another person I would mention just really quickly, this guy J.J. Thomson, he's given credit for discovering electrons. He used a device called the cathode ray tube. The cathode ray tube is basically the forerunner of televisions, actually. When you put a power supply through here, electrons will cause the screen to light up. And what he discovered is using a magnet, you could actually, so like if he places a magnet under here, he can cause this stream to bend. So he knew there was something kind of moving through the stream, through the screen to cause it to light up. There was some sort of particle, and he could affect it by a magnet. Therefore, it had a charge. So he realized that electrons exist in that way. And so that was the way that people thought about atoms for a while. We've got now what we've added to the model is there's electrons, so it's improved upon Dalton's model, but still not perfect because people didn't know about the nucleus and some other stuff that we're going to talk about. So here's a picture of his model. Again, it's a cloud of positive charge, because there has to be positive charge to cancel out the negative from the electrons, and the electrons are kind of just dispersed through. Again, not correct as we'd view it today, but an improvement upon Dalton's model. So Ernest Rutherford conducted the gold foil experiment, one of the most famous experiments in all of science. He is given credit for discovering the nucleus. He discovered or said that atoms were mostly empty space. Now, some modern-day physicists might quibble a little bit with what exactly we mean by empty space, but let's leave that aside for right now. And nearly all of the mass is in the nucleus. So an analogy I've heard is like this. If the atom were the size of a football stadium, the nucleus would only be the size of a tennis ball. And the tennis ball would be in the center of the stadium, the electrons are sort of whizzing around on the upper deck. So that gives you a size, the idea of the size of the nucleus compared to the rest of the atom. And all that other area would be empty space. Now, we have a hard time wrapping our brain around empty space. I'm not talking about air. I'm talking about nothing at all. So what's weird about this is if you think about it, since atoms are mostly empty space, that means you and your pencil and the chair you're sitting in and all that stuff is also mostly empty space, despite what it sort of looks like, despite what we perceive it as. Shocking, but he does have a good reason for this. Like I said, the gold foil experiment. So let me just tell you about it very briefly. What he did, or actually what he did, is he made some of his students do this because he thought it was going to be a boring experiment, and it was. It was a boring experiment, but the results were extraordinary. He had a really thin sheet of gold foil, and he was firing alpha particles at it. Now, alpha particles, as we now know, are a type of radiation. They're actually a helium nucleus. And they're coming out of this thing, and they were shooting at the sheet of gold foil. And what he expected was, if the Thomson model of an atom is true, basically all the alpha particles should just pass right through the gold foil, because there's really nothing for them to hit in the Thomson model. But what he found that was very shocking is most of them, almost all of them, actually did pass straight through the gold foil, completely unaltered by it. But a small percentage of them were deflected from their pathway a little bit, and some of them even bounced straight backwards and kind of hit the detector here. So the scientists recording this could see on this little detector where the alpha particles were hitting. So that was super surprising. And let me show you a cross section here. And so this is what Rutherford deduced after thinking about this experiment a little bit. So here's a cross section of these gold foil atoms. So this is the gold atom, this is the nucleus. If this were to scale, the nucleus would be even smaller than this. The nucleus would be invisible at this scale. So these are actually exaggerated in size. So the alpha particles were coming through here. Almost all of them were just going straight through because they were missing all the nuclei, because nuclei are very small. And a small percentage of them were deflected. So if an alpha particle comes in through here, it might be bent a little bit by the nucleus. So from this, Rutherford knew that the nucleus contained positiveness. The reason for that is because the alpha particles are positive, and the alpha particle being repelled, being pushed away from the nucleus. So therefore, since like charge is repelled, the nucleus must have positiveness in it. And the nucleus must also be very small because the vast majority of the alpha particles were missing it completely. And it also must be very sort of heavy and dense because on very rare occasions, an alpha particle would strike the nucleus directly and be bounced straight back. So the nucleus must be a significant kind of concentrated amount of mass that the things are hitting. So after this, we knew a lot about the nucleus, and kind of a lot of the basic structure of the nucleus was in place. So this is the part right here. We're going to kind of leave the nature of science stuff aside for right now. This is the important stuff. This is the stuff that you certainly need to know. I would write it down in your notes. Let's talk about sort of our modern view of the atom. And I've left out a lot of important scientists here, but let's talk about our modern view of the atom and what we think and about it right now. So a lot of this you've probably heard before, but understand that we're going to kind of come at this at a new level of detail, and it's very important to really precisely understand this and understand some of the terminology here. So the nucleus, as we've just been talking about, it contains protons and neutrons inside of it. Collectively, you can use the word nucleons to refer to both protons and neutrons, so that might be a new term for you. And as we've said, the nucleus contains nearly all of the mass of the atom. It's very small compared to the atom as a whole. If we define the atom by where the outermost area where we find the electrons, it's very small compared to that. Protons and neutrons have about the same mass, which is about 1 AMU. We're going to talk about that AMU stuff a little bit later, but just know they have about the same mass. Protons have a positive 1 charge, but neutrons are neutral. It is protons that give an element its identity. Each element has a unique number of protons. Now let's talk about the word unique for a second. A lot of people use the word unique incorrectly. If we're using the word unique correctly, you can't be just a little bit unique. It's like being a little pregnant. You can't be a little pregnant. You either are pregnant or you aren't. And you either are unique or you are not unique. If something is unique, it means one of a kind. So if we're using the word unique properly, each element contains a unique number of protons, meaning hydrogen, for example, has 1 proton. So atoms with 1 proton are hydrogen, period. Carbon contains 6 protons, so atoms with 6 protons are carbon, period. So it is the protons that give an element its identity. And each element has a unique number of protons. Electrons surround the nucleus in regions called orbitals. Now, most of chemistry really involves electrons and rearrangement of electrons, so we're going to talk about electrons in a lot of detail. So we're going to talk about that later, but we'll just say for now they exist in these regions called orbitals. Electrons have a -1 charge, and they are much smaller than protons and neutrons, about 2,000 times smaller, and their mass can be considered negligible. Now, if negligible is not a term that's in your vocabulary, let's get it in your vocabulary. Negligible means something is very, basically it means things that can be ignored. We don't have to worry about it. So electrons are so small, we don't need to worry about them compared to the mass of a proton. We'll just check in here with Mr. Dog. I think he likes it. I think he's enjoying the video so far. I hope you guys are as well. Okay. Thank you, Mr. Dog. We really appreciate that. Good to hear from you. Let's talk about some other terminology. Isotopes are atoms with the same number of protons but a differing number of neutrons. So IB is very, very particular about how we use language, and if we define something, we need to be very precise with our language. If you were asked to define isotopes on an exam, in either the IB exam itself or an exam in this class, you would pretty much need to use that exact language. Let's kind of talk about isotopes a little bit, and then we can kind of go back and dissect this definition a little bit. But basically, isotopes are all the different versions of the same element. You know, for example, your body has many, many billions and billions and billions of carbon atoms in it. Some of the atoms are carbon-12, which have 6 protons and 6 neutrons. Some of the atoms are carbon-14, which have 6 protons and 8 neutrons. There is absolutely no difference between the two of them to your body, or in any chemical reaction they're going to behave exactly the same. It's just the number of neutrons that are different. So most elements have a number of different isotopes that are naturally occurring, and in any given, you know, if I take a piece of iron, for example, there's going to be several different iron isotopes sort of all mixed in there, and most all elements are that way. Some isotopes of certain elements are radioactive, which means they kind of give off particles and they decay over time. We're going to talk more about that later, but let's just say that some are radioactive. And as I said, isotopes of an element have identical chemical properties. So in all chemical reactions, they behave totally the same. Isotopes would vary just slightly in certain physical properties like density or boiling point. And like I said, a sample of any given element is going to contain a mixture of all its isotopes. So you got a chunk of iron there. There's going to be several different iron isotopes in it, kind of all mixed together in different amounts. Now, it is actually extremely difficult to separate isotopes. So you take this chunk of iron to actually separate it into the different isotopes. It can be done. It's not easy and is almost never done, actually. But if you, for some reason, did that, separated 2 different isotopes of iron, you would find that they behave exactly the same in chemical reactions. But if you tested their density, if you tested their boiling point, their melting point, there might be very slight differences in there. So going back to this definition for a second, let me show you, let me give you an example of some things that in IB and me would count wrong if you did this, if you said this definition differently. Like, for example, if you said isotopes are elements with differing numbers of neutrons, they would count that wrong because it is kind of picky, but if you think about it, it's atoms that have neutrons, not really elements per se. Elements are made of atoms. So things like that. We just need to be really careful with our definition. So another term is ions. Ions is a term for charged particles. The way things get a charge is so remember, only electrons and protons have charges, right? But it is changing of electrons that cause things to get a charge. The nucleus doesn't really change in chemical reactions. So you get a charge by gaining or losing electrons. If you use the term atom, if I say, for example, an atom of iron or an atom of sodium, if I'm using the word correctly, I'm referring to something that's neutral, that has no charge. So in that case, in atoms, protons, the number of protons and the number of electrons is going to be the same, since protons are positive and electrons are negative. Atoms have the same number of protons and electrons. Ions will have a different number of protons and electrons. So let's talk about some of the symbols here and kind of the way that isotopes can be represented. I would maybe jot this down, this symbol here. So in this position is going to be the element symbol. This number at the top is going to be the mass number. And actually, let me pop these definitions up. There we go. These are definitions that you need to know. Mass number is the number of protons plus neutrons. That goes up here. The atomic number is down here, which is the number of protons. If a particular thing has a charge, it'll appear up here, and so that would be the element. These two symbols, Z and A, are, again, that might be, even if you've studied atoms before, that part might be unfamiliar to you, but you should know that the atomic number is Z and the mass number is A. So here's kind of a generic one, and like I said, I would maybe jot that down just so you know. And we'll talk about more about interpreting these symbols. It's pretty easy, but from these symbols you can always determine the number of protons, electrons, and neutrons. And here's one, a real one, like this is magnesium, mass number 24, and atomic number is 12. And this one has a charge of +2. So if there is a charge, it'll be up there. Sometimes in the IB world, I think actually more often than not, they won't have this number here because it's redundant information. And the reason that is the case is because magnesium always has 12 protons, so that doesn't need to be put down there once we have the symbol. One more thing I just want to, or a couple more things here, but I just want to mention sometimes you'll see carbon-14 or, I don't know, chlorine-37 or whatever. When you see that, this second number is the mass number, so just don't be thrown off by that, and know that when I say carbon-14, I mean carbon with a mass number of 14. So that's another way to communicate the mass number of a particular isotope. Okay, so let's talk about relative atomic mass. Relative atomic mass is the weighted average of all isotopes of an atom compared to 1/12 of a carbon-12 atom. Okay, so that's a little wordy. Let's break that down. Basically, the decimal number that you see on the periodic table is an average mass of all of the isotopes of a particular atom. So like I said, a chunk of gold is going to contain several different isotopes of gold, all mixed together. So that mass that you see on the table is an average of all of the isotopes. Weighted average meaning it's averaged in proportion to how common that isotope is. And we'll talk about this more in class and exactly how it's done and calculated. So you need a unit to weigh atoms in, or you need a way to weigh them. So there's a device called a mass spectrometer. And basically what that can do is it can actually separate isotopes, separate an element into its different isotopes of the different atoms. So you need a unit, and it was determined that 1/12 of a carbon-12 atom, now carbon-12 has 6 protons and 6 neutrons, 1/12 of a carbon-12 atom would be 1. That would be considered to be 1. Now, in most of the world that I'm familiar with, they call it an atomic mass unit, an AMU, but IB considers the value to be unitless. So, and they will ask you about that specifically, by the way, sometimes, where this mass comes from. So we just sort of arbitrarily say, okay, 1/12 of a carbon-12 atom is going to be 1, and we're going to compare every other thing to that. So therefore, since carbon-12 has 12 nucleons, protons and neutrons both weigh about 1 AMU, and then we're comparing all of their masses to that. Again, IB considers it unitless. So these are what appear on the periodic table. Those numbers in the periodic table are an average. When we see chlorine's mass, which is like 35.45, there are no chlorine atoms that have a mass of 35.45. It's just like when you say the average American family has, 1.7 kids. There are no families with 1.7 kids. It's just an average. Same thing with those masses in the periodic table. Those are not the masses of individual isotopes. There are no atoms with those masses. It's because there's an overall average of all of the masses. And again, we're going to talk more about this. You can do some calculations. They're pretty easy. I'm sure we can get them figured out. But I think that looks like it's just about it. Thank you so much for watching and listening, and we'll see you next time.